So like a Dawn Cicada chorus, let's start right on time here. Welcome everybody to our second BioAcousTalks of spring 2025. And today I am super excited to welcome Francisco Rivas Fuenzalida, who just 2 weeks ago, I think, defended his PhD at Purdue's Center for Global Soundscapes, which is where I also did my PhD. So congrats again, Francisco. Huge achievement. And yeah, he will be sharing with us this. Yeah, let's give it some hearts and party emojis. Um, he came into grad school not knowing how to code, coming from a career in music, and I guess at some point got inspired by nature's original rhythm section, insects, and built quite a comprehensive Rpackage that is usable, interactive, has different ways of measuring sound, and in an interface that non-coders can use. So hopefully this is a real game changer for people interested in doing insect bioacoustics, and super eager to hear more about it. So Francisco, welcome. Everybody, if you have questions during the talk, we have a Q&A button down below that you can put any questions there that we can try to answer, or if not, we'll come back to them at the end of the session. So with that, let's learn about Rthoptera.
Thank you, Ben. Hi, everybody. Thank you for joining. My name is Francisco. I am from Chile. And as Ben said, I just defended my PhD dissertation at Purdue University. And I'm going to tell you about Rthoptera, which is an R package for insect bioacoustics. But first, I'm going to tell you a little story about this, how I got interested in insect bioacoustics and how finally ended up developing this package. So when I was in Chile, I was a music teacher. I was a music teacher for 7 years, and I started a project called Museo Bioacústico, like in this logo here, um, for outreach of the sounds of nature, basically. And I was very into birds at that moment, so I recorded a lot of birds along with my friends and colleagues. Working on the summers on that. And then after the birds stopped singing, I was kind of bored because I didn't have anything to record. Insects for me at that time were just noise, background noise. But then I realized that for our project, we needed to record insects because we didn't have any sounds of insects. There's not a lot of people doing bioacoustics in Chile anyway. Um, so I asked the bug nerds in Facebook in Chile who were the people who know about the sounds of insects, and they told me nobody. So there's a couple of experts in Orthoptera. They work in universities and museums, but they work with morphological data, with mostly dead specimens. So I had it to start from scratch. At the beginning, I thought, "Oh my God, this is too much. I cannot do this, or I'm not interested." But then I realized that it was super fun to do because you were discovering something new, right? So that's why I got interested in insects, and then it became an obsession soon after. And then when I tried to analyze the sounds, I realized that you don't have a lot of tools to do the specific measurements that you need to do in order to describe the sounds of insects. Or if you have them, some of this software is proprietary software. You have to pay for it, or you have to use multiple tools to create what you need, right? So I was very frustrated, and when I came here, I started learning R, and then I realized that this was the right tool to do it because you already have packages capable of processing audio signals, and all you have to do is put together the pieces, right? So that's the story behind the package. Um, okay, so insects, as you might know, are essential for most terrestrial ecosystems, if not all of them. So monitoring their populations is of critical importance for conservation in general. Um, and for that, some of these insects makes this work easier because they make sound. So you don't have to actually see them to know where they are. So we can use bioacoustics tools to assess their presence, the population, trends, the systematics, meaning the taxonomic relationships between the species and populations, evolution, etc. But the problem, as I was saying, is that the analysis of these sound signals is not fully standardized. And also, you have a lot of different software that are not specific for this kind of signals. So you have to adapt all the procedures, and it's time consuming when you use different software at the same time. Some of them you have to pay for them, and there are some fine-tuned parameters that, because these tools are not designed for acoustic signals of insects, people generally just don't measure. So I'm gonna share here just a couple of examples from the literature in the last couple of years. These are the kind of plots that are used in insect bioacoustics. You have the oscillogram here in letter C and B, spectral power or power density on D, and the spectrogram um, on letter E. So we have several issues with this kind of plots, because sometimes when you measure the signals, a lot of researchers do it manually, right? Like here in this section of the methods. Um, and they use custom scripts or proprietary software to create the plots. Same case here. They use MATLAB, which is you have to pay for that software. Um, and they say here each chirp was individually extracted for analysis, probably manually. They didn't specify here. If some of the authors is present, it would be nice to know. But I've heard a lot of stories by colleagues that they manually select signals to analyze, and that takes a lot of time. Uh, Again, proprietary software. And here, for example, this signal is kind of wavy in general, because maybe we needed to apply high pass filter to get rid of the low noise that creates these waves that are not part of the signal of interest, and so on. So we need an accessible and flexible tool to do this job. We need to develop as a community standardized procedures, and also some metrics that allow us to explore the microdiversity in acoustic signals, for example, to identify individuals, assess the diversity in acoustic signals within a population or between populations, etc. So what is Rthoptera? Rthoptera is an R package for insect bioacoustics. For those of you who don't know, R is a programming language which was developed initially for statistical analysis and plotting, but now you can do almost whatever you want in terms of research um, and analysis in this software. And it's also a collection of 17 Shiny applications. So um, Klaus actually, when I was starting developing this, he mentioned that it would be nice to have some Shiny applications for these functions, because not everybody is knowledgeable about R, or they're just starting out, and the adoption of this tool would be easier if you have an interface, user interface, like Shiny provides. So this is one example of a Shiny application available in Rthoptera to create this, what I call multi-plots, because it's three plots in one. So if you select a wave object that you have already imported, we're going to do a demonstration afterwards. You select a wave that is already in the R environment. You can stick with the defaults here, and with one click, you have all these three plots perfectly aligned. You can also leverage the Plotly package. So this is a function to create an interactive spectrogram, um, and you can change the colors, whatever, right? Um, the good thing about this is that if you save an interactive spectrogram, the users or the readers of your article are going to be able to explore the spectrogram in any detail they want. Um, so that's an advantage. Then the classic spectrum plot, which most of the time people do the mean power spectrum, but you can select different functions. For example, here the SD, um, the standard deviation of this of the energy in the spectrogram, which I think it's convenient when you have some background noise, because it allows you to see where the diversity in amplitude is occurring, right? Where the actual sound is occurring. Um, you can also color code oscillograms, which is convenient when you want to point out, for example, different individuals in the same recording or different type of sounds in the same recording. And it has a palette of colorblind safe colors. Researchers also tend to use multiple oscillograms stacked upon each other to represent different signals or different species. You can do this here as well. You can also use multiple power spectrums or spectra of the same signal. So you can have different parts of the calling song of an insect, for example, and uh, see the power spectra of all at the same time. You can control the opacity. I'm going to demonstrate that later. And this is an interactive version of that. So the previous one, this one is a ggplot. For those of you familiar with ggplots, are static plots, which are more suitable for um, the physical version or the digital static version of the manuscript on a PDF, for example. But this one, you can make it accessible to your readers through online repository, and this is an HTML document. The output is an HTML document, and they can again explore and zoom in, zoom out this power spectra. Similar to the previous one, you have zooming oscillograms, where you can select a portion of the main oscillogram and zoom in. For now, it's just two zoomed in oscillograms that you can stack. Maybe if people need more, we can do that as well. And we also have new metrics that allow us to summarize the sounds of insects. In this case, um, I'm going to present the pattern complexity index, which is temporal measurements of trains and gaps in. So I'm going to roll back a little bit because you know that in insect bioacoustics, we have a lot of um, dichotomous nomenclature and terminology, right? So I opted to use an agnostic terminology, which doesn't reference the behavior, right? Because you have, for example, syllable, dipple syllable, hemisyllable, which refers to the movement of the forewings or the tegmina, right? But you don't always know that. Sometimes it's too fast, and you don't have like a slow motion camera or another device to detect that, opto device to detect that. So we opted for this behavior agnostic terminology, in which A peak is the smallest unit, which represents most of the time the sound produced by one tooth of the stridulatory file against the scraper. And then a group of peaks is a train, right? And this is sometimes created by one motion of the techmina, and sometimes uh, two different trains is created by the same direction because they add pauses in between. So to avoid that complexity with the behavioral terminology, we use this agnostic terminology. So the pattern complexity index basically try to measure the structure, the temporal structure of a signal, of a calling song, for example, um, by controlling for the duration and also yeah, the number of trains in the motif, right? Motif is synonymous of mostly of Kim. So you first measure the trains and the gaps in a call, and then you take the proportions of those, and then you calculate the pattern complexity index as follows, with the Shannon entropy of the proportion times the coefficient of variation plus the number of trains, the root square of the number of trains in a motif, normalized by the duration of the motif. So basically, longer call will tend to have a higher PCI, but this will be reduced if the call is repetitive, right? If the durations and the gaps are more or less even across the call. Whereas shorter calls with a lot of different gaps and durations of the trains is gonna tend to go up in the PCI. So the temporal excursion is meant to measure differences in the time of the peaks or the tooth impacts, if you will. So first you detect the amplitude peaks in the envelope, and then you compute the time deltas, and then you sum the absolute values of those. So I'm going to explain that in a bit. Then the dynamic excursion is a similar idea, but you do the calculation of the differences in amplitude across a single train. So here we have one call, very simple call of Phaneropterinae cricket from Chile, katydid from Chile, and this signal people generally wouldn't be able to measure it in this way if we use the classic threshold approach, because if you see the first train here, or hemisyllable if you will, is super faint, and it's so faint that is lower in amplitude than uh, this part of this final train that is has a higher amplitude, right? Because in the when you apply the envelope, all these differences in the lower part get kind of blurred, right? Because you have reverberation. So traditionally, you will have to measure or this last part or the first part of the call. So we have another algorithm here to measure the peaks. Instead, for low quality factor signals, which are the ones that are like broadband signals, like those of most katydids, and then you can measure each peak. And this allows us to create these other metrics that are very useful. Um, for example, the first train here, the faintest one, has the highest temporal excursion because you have an acceleration here. So this is like decelerating and then accelerating again. That creates a high temporal excursion value. Whereas in the other two, you have a higher amplitude, but the temporal differences between the periods of between the peaks is lower, right? Because it's more even. On the other hand, you have the the dynamic excursion is higher in the last peak, right? Because you have all this range of amplitudes, whereas in this other two, it's very low. Okay, and well, this is how you launch the apps, um, which we're going to see in the demonstration after. You just type launch app and then you type the name of the app. So the song statistics HQ, we have two ways of obtaining the song statistics, which the HQ, high quality factor signals, like most of crickets. You can also use it for katydids, certainly. But sometimes, if you want to calculate all this other temporal excursion and dynamic excursion, you're not going to get it with this one. In the future, I plan to adapt that calculation to create a temporal excursion and dynamic excursion value to the motif or Ekim level, but that's not the case as of now. Um, so yeah, so if you have cricket sounds that are very easy to measure with a threshold approach like this one, which is the classic approach to detect signals, you're gonna use this application. So you run the analysis and you have a bunch of tables with a summary, with a table for the motive or Ekim durations and PCI and so on. And for each train, also you have that table for the trains and for the peaks. So it's a lot of data. And if you want to do other calculations, you can work on those tables to perform your own calculations. On the other hand, if you have very high quality recordings, not high quality factor, high quality recordings, very high signal to noise ratio, and you want to measure the within the train the the dynamic excursion, the temporal excursion, and so on, you're going to use the song statistics LQ, low quality factor, and that is going to give you an extra table with each of the peaks, the position in time of each of the peaks, the amplitude of each of the peaks, and so on. So regarding the equipment, I think it's not directly related to the software, but it has some consequences. So we have been discussing with some colleagues about the equipment to use. I was advised against using this. Let me see the laser. So this is a shotgun microphone. The capsule of the microphone is here on the bottom, so you have a lot of distance between the longer the shotgun, the longer the distance between the capsule and the insect, right? If you even if you're very close to the insect, I was advised to use omnidirectional short microphones because you can place them shorter at a shorter distance. We also use these bat detectors to, especially for those insects that stridulate very high frequencies, ultrasonic frequencies, especially. Um, and I also was advised against using parabolic reflectors. But I'm here to discuss, and we can we can talk about this later with the experts. If you want to do a very detailed temporal analysis, I would recommend using this, for example, the parabolic reflector, or using these microphones and going as close as you can with to the insect, no matter if you get saturated signal, because you can use another microphone or use another recording to do the spectral analysis. But for the temporal analysis, especially if you want to measure the within train peaks, you're gonna need a very good recording. So yeah, so I'm open to discuss that later, and also you're gonna try to use this latest recorders that allow you to recording 32-bit float, because the dynamic range of those is better. So maybe we can work with some of you in technical uh, white paper or something to compare what's the result of these metrics, automated metrics with different equipment. So, in conclusion, Rthoptera offers an efficient workflow, avoiding using multiple softwares simultaneously, standardized plotting, semi-automated measurements, and new metrics relevant for insect bioacoustics, as I mentioned before. And also with the convenience that we have interactive, shiny apps for the convenience of people who are not very familiar with R. So now, yeah, and we have a how do you call this, GitHub page for Arthoptera, where you can browse the articles and tutorials on how to do um, the analysis. So now I'm going to. I don't know if there's some questions now between now and the demonstration. I'm going to do a little demonstration now. So if you have some questions, I'm happy to answer them.
Yeah, that sounds great. Why don't we um take get off the highway to a rest stop, or yeah, see if anybody has any questions up to this point for Francisco about what he's covered so far. Yes, Klaus.
Do you hear me?
Yes.
Yes.
Yeah, okay. Just a remark to the first great talk and great tool, and I'm looking forward to work with that. I must admit that I always was too lazy to learn R because then you don't use it for 2 weeks and you forget everything. But with the Shiny app, I really have a chance. So your remarks about the recording equipment, uh, just a little adding, which might be relevant also for the BioAcousTalks community.
Mm-hmm.
Personally, I'm working now with AudioMorph, and I understand that a lot of the audience here is also working with AudioMorph and working with echo acoustics. So that's sort of the contrary of the dedicated, clear-cut, high-quality recordings you just presented. But
Mm-hmm.
I think your Rthoptera software is also good for these more lousy recordings. Maybe not every aspect, and my vision is to extract sort of stable features, simple features,
Mm-hmm.
uh, which are also relevant for the insect itself, because the insect itself listens under most distinct conditions.
Yeah.
And so somewhere in these signals, there must be simple features which are relevant for the insect and which are also relevant for the researcher to classify a call and identify it without going in too much details. So
Mm-hmm.
I just wanted to point out the difference between these echoacoustics recordings where you can filter out certain insect elements and what you just presented about the high quality thing.
Mm-hmm. Yeah, we have to bridge that gap between the the detailed bioacoustic analysis and the ecoacoustic analysis. So yeah, Orthoptera was meant to analyze type, the acoustic type of a species, meaning the first description of the sound of that species, right? Papers that you usually present in the Bioacoustics journal or something like that. Um, and which will be the basis for identification afterwards, um, before creating the automated detectors. So there's a couple of steps in between that we should discuss as well. So yeah, experience Zoom F3, Tascam, Frav. I haven't tested the Tascam. I haven't tried the Tascam Frav, but I know that it's capable of 32 bit. That's why I suggested that you can use that one. Um, Okay, so if you go to R, you're
I
gonna
see,
see our studio.
sorry,
Sorry.
Francisco, I see a few more questions that
Okay, good.
useful now. One is, can this package be used for other taxa besides insects?
Yeah, you can. I mean, if you want to extract only the temporal structure of a signal and also the frequency metrics, you can do that. And it's also useful for plotting. But yeah, it was meant for insect bioacoustics, but the functions can also be used for the
Right.
other taxa.
Yeah, and there's lots of taxa that produce like pulse trains, like certain amphibian species,
Right.
certain species of fish. Yeah, I think definitely there are some sort of universal features of this tool that will be useful to a much wider community than just like the hardcore insect bioacousticians.
Mm-hmm.
And I really like Klaus's question of figuring out what are these stable features
Yeah.
that you can capture in a super high quality field recording, but for all of us working to identify insect species in passive acoustic recordings, which of those features are still detectable from at a distance
Yeah.
and also in a noisy soundscape. So I think that's a really cool opportunity for some studies there.
Mm-hmm.
And any other questions? There's one about hemisyllables. And now I'm out of my depth, but how effective is this method in identifying and distinguishing closely related or sympatric species? And maybe let us know what a hemisyllable is again, just to, so we're all on the same page.
Yeah, so hemisyllables are so when the insect creates sounds, most of these katydids, for example, they create sound both when they open and when they close the tegmina or the wings, the forewings, right? So a hemisyllable is half of that sound. Like when you open, that's a
Mhm.
hemisyllable. When you close, that's another hemisyllable. And both together, some people call them diplosyllables or diplo. I don't know how to pronounce that. But yeah, so it's a very detailed analysis of each of these units. So how reliable and defined? It depends, right? Because so I've seen we're working with some insects in Chile now, and we have discovered cryptic species. So morphologically they look the same, but they make different sounds. And in one of them, they make almost the same acoustic pattern temporally, but the amplitude patterns of each of these hemisyllables might be different. I have not done that analysis yet because I need better recordings. And that's why I emphasized that when you want to do this very detailed work, you need very high quality recordings. Or sometimes you have a noise in the background that is low pitch and it's not part of the signal. So I'm gonna demonstrate here right away, so you can take a look at how this might work.
Perfect.
So um, I'm going to so in our studio you have um, a script view, the environment, the console. Whatever you write in the console is not gonna get saved anywhere. So if you want to save your work, you can use a script. So I'm gonna open the package. Library Rthoptera. Control Enter. And then I'm gonna open the companion package with the example sounds. How are we in time, Ben?
We have 25 minutes until the hour.
Okay.
And we can always go a few minutes extra if you have the time.
Okay. So I'm gonna load some of these sounds from the Rthoptera sounds package with the data command. Let's do Codifoda and Grillos, just these two. Okay, so when you want to use a Shiny app, you have to type what's the command? Launch app. If you don't know the name of the app, you can just run this and it's going to list all the apps available. So we have apps for importing and pre-processing sounds. So if you have sounds in your computer that you want to import and you don't want to type the commands for doing that, you can use imports. And it has pattern matching. So if you have a word in a function that is not in the other functions, you don't have to type the whole name of the function. I need to hide. Okay. So you browse here, your computer. Um, and you have to name it. And that's it. That's how you import audio with Rthoptera. And now you can see the audio in the environment. So let's do some plots, for example. Please comment on the make comments here to if you want me to go through a specific function or app. I'm not gonna. I don't see the comments, so Ben, if you can help me with that.
Sure, I'll be monitoring.
Multi plots. So this is gonna open this Shiny app, and you here select the waves. These are the waves that are already imported into R.
Just to be sure, do you have two R windows open?
Oh, you're not seeing? Okay, I'm gonna share the whole. Wait. Yeah, it's a pop-up window, so maybe I
Yeah,
have to
we
share
don't
it
see
again.
that currently.
And I don't see the share button. Where's my panel?
I would stop sharing and then
Yeah, but
start
I don't
sharing.
see. I hit the panel and now I don't know how to open it again. Ah.
That's okay. It's just building anticipation. I just watched Michael Jackson's 1992 Super Bowl performance, and he was up on stage for 2 minutes, completely frozen, and the crowd was just, he said it's important to build the anticipation for
Yeah,
seconds.
but I'm not finding the freaking uh panel here. Where's the panel?
Um, Here, I'm stopping you from sharing.
Maybe I just have to. Okay. All right. Thank you. Share the screen, right?
Yes.
Maybe now it works. Do you see the pop-up window now?
Yep, looks great.
Yes.
All right. Thanks. All right. So yeah, this is the multi-plot. So I'm gonna select the Codifoda, which is a short song. And with one click, you just wait a little bit. And you have the multi-plot already. You can change the scale to have a decibel scale here on the right hand, and you can change the height, the relative height of the oscillogram relative to the spectrogram before you save the PNG file. You can also choose a transparent background if you want to use it in a fancy way. and you just close the app as that. Let's do the analysis. So I'm gonna launch app song stats low Q because I want to measure the peaks. So I'm gonna open the Rthoptera. You can add here a specimen ID to save both in the table and in the plots. Okay, so I have to change. So you have to modify the parameters based on what you're measuring, right? So the detection threshold is going to be what is the minimum amplitude that you want to detect. So let's do 0.5, maybe 0.05 here. If I want to detect the first train. Yeah. So you see now that you have the second train, but you're not detecting the first train. Maybe you have to do this sometimes when you have noise in the background. But in this case, this is a very clean recording. So I'm going to go down a little bit more to detect the peaks on the first train. And there you go. So the good thing about these plots is that they are interactive on their own. So you can zoom in and you can see kind of the quality of the detections, right? So I think this is enough. I have most of the peaks detected. And then you can go auto scale to reset the view. So the peaks are going to be these orange dots. Then the grouping of the peaks is going to be the trains, which maybe you're going to translate it as hemisyllables. And then the motive, you are going to translate it as a keme, for example, or phrase. And if you have groupings of chemes, you can do motif sequences. So for each of these, you're going to have a table. So this is just a very short stridulation, and you have all this data. And you also have a table with the parameters that you used, so you don't forget or you don't have to annotate separately, right? You have all this information that you're gonna use in the methods section, right? What parameters you use for the analysis, um, number of peaks per each train, etc. So if you have any questions about this one, I'm happy to answer. You can toggle on and off each of the graphic parameters here as well. Even the envelope, you can get rid of the envelope and just see this.
Is there a way to manually correct, like if it doesn't realize that there's a train or it connects two trains, that you can go
So
in?
you control that here. So for example, if you want to connect these three in a single train, you're gonna have to change this parameter. So each of the parameters here have an information icon
Great.
explaining what is for. So in this case, you select the maximum gap between peaks for them to be considered in the same train. So if I increase this by, say, this is 100 milliseconds.
As this is loading, one question that I think would be useful. So I imagine I certainly am going to give this a try. If for people who try this and maybe see bugs, pun intended,
Yeah.
or have certain features that they think would be really cool, what's the best way to pass that information? Is it in the GitHub page?
Yes. So if you go to GitHub, Nature Waves, Rthoptera, this website here, I'm gonna
Mhm.
copy and paste it in the.
I think it's already in the chat.
Oh, really?
Hmm.
Okay.
Yeah.
Okay, cool. So here you go to issues, and here is where you can report bugs and suggest new functionalities. So I'm very open to collaborate with other people who they have maybe their own script for their small analysis they want to do or they used to do, and maybe it would be useful for us to incorporate it in the package as well.
Excellent.
So okay, let's go to the next one. Oh, you can also do um, spectral stats. So the song stats that capture the temporal patterns, they also, for each of the trains, calculate the peak frequency, the minimum frequency, the maximum frequency, and so on. But you can control those better if you do the spectral analysis separate for the whole call. So there's are some fields that you want to add maybe just to have a record of all the environment variables. I'm just making this up, and this is very fast, as you know, as you realize. It's in a very short time you have all these parameters here, and you can visualize also the mean spectrum interactively. So maybe you can if you want to measure the whole extent of a call, regardless of the gaps that are in between here. So I'm gonna do decibel threshold -6, and I'm gonna do total bandwidth. This is what you get. If you don't do so, the robust analysis uses a fixed frequency resolution of 244 hertz to reflect like the broad structure of the call, spectral structure of the call. But if you don't, you're gonna have a more detailed spectrum like this. This is a bug here with the colors, uh, and this is what you're measuring when you use the total bandwidth. It's gonna ignore these gaps here, so it's gonna detect the minimum frequency the first time that the spectrum crosses the threshold, and the maximum frequency will be the last time it crosses the threshold. So it's not very convenient if you want to measure a katydid song to use um, non-robust analysis, because it's gonna just pick up the a very narrow part of the frequency spectrum. You can solve that by doing the total analysis. Um, it's gonna be a little bit better. You can change the threshold as well. So some of us like to do -20, um, and then you can cover like a wider proportion of the call. But I think this robust parameter here is very useful because it kind of evens out the differences in the recording equipment that you use. And that is why it's more robust than the other approach. Spectral statistics and other measure.
I've got,
Long files, no, please
yeah,
don't.
okay.
It's gonna take forever because it's a lot of uh, R. I don't think it's meant to deal with that amount of data, because in audio you have, if you use a high sampling rate like you usually do for insects, and you have long recordings, it's
Boy,
an insane amount of data.
What about Francisco, in the case where maybe you have 200 high quality short clips of
Mhm.
insects? Maybe you've done a longer recording and you've automatically segmented and found the pulses, and you want to conduct a pulse train and analysis or temporal analysis. Do you have a way of, just looping through some of these, using some of these functions, maybe either to create a graph and save it for each file in a loop, or even without visualizing, just give me all of that detailed information for hundreds of files?
Yeah.
That's not
So
something you do one by one.
all the functions, all the apps in Rthoptera are also regular R functions. So you can also create a loop to run a function in a batch mode, but it's not implemented interactively yet. So that's it's gonna be in the to-do list. But if you know a little bit of R, you can do your loops with regular functions, right?
Great.
Um, is there any other questions that I didn't address?
Um, Another question related to just how much does the quality of the recording matter for the usability of this function? I'm also curious if you were able to validate or compare the acoustic measurements in this program with other established tools,
Hmm.
like what's available in MATLAB or in Raven. Like, have you gotten the same measurements using these different um, approaches?
Yeah, well, the only things I've tried, because they are compatible, are like the frequency measurements, because most people at least in the papers that I've read, do the temporal measurements manually,
Mm-hmm.
right? Or they use threshold detector.
Right. I guess a
Um,
better question for me is, if this is an automated tool that's replacing what used to be done manually, have you
mhm.
done a lot of verification between this automated tool and manually going through the insect sounds, and to what degree have you validated this tool and its different measurements?
So mm, I haven't conducted like thorough, or yeah, large scale validation of the manual measurements, because that's why I developed this package, to not do the manual measurements.
Yeah.
But so that's why this package has the interactive visualizations. When you do the measurements of the temporal features, for example, you're always going to see what you're measuring, so you can adjust the parameters and so on. So that's mostly how I have assessed the the measurements visually with the plots. But you're welcome to try it, and you can publish a paper on that.
Yeah.
I'm not gonna do it. So this one is for um, visualizing the the mean
Wow.
power spectra of different selections. Okay, so I'm gonna do it again because I messed up. So I'm gonna use the 512. You can name this as well for the interactive plot. So I know that this one, because I studied this insect, I know this is the closing hemisyllable. So I'm just gonna leave this here, You can also create your own labels because sometimes you want to point out something different, right? Here the defaults are open, closing, male, female, and custom. You can enter your own. So this is closing. This is also closing in this insect. And this is opening. And then you have this, and you can toggle them on and off. And this is the final plot is still interactive. So that's the advantage of it, and you can explore the different portions of the signal. It's going to tell you the amplitude of each of the signals along the spectrum. And you can change also the opacity here. Oh, I'm gonna have to do it again. So this to work with the same colors, you have to reset the whole application. But you get the idea, right? You can select the opacity, and you have the different tags that you can select here for the multi-main spectrum. Is there any other? We can also do some editing here. So just to avoid the multi-package, and I wrapped some functions from other packages like C-Wave to edit interactively the waves. So for example, bandpass filter, you can do a bandpass filter here. Let's see. Well, this is clean. Maybe this one. Well, anyway, imagine that you have some noise here. You can zoom in to see where the noise is, what's the frequency of the noise, and then you can do a high pass filter, for example. This would be destructive. Imagine that this is the noise, for example. This is the signal, of course. But imagine that this is the noise. You do a high pass filter, and then you don't have that noise anymore, and you have the signal of interest only. And you can save it with the same name, which would overwrite the wave, or you can add another name. And it's going to show up in your environment here.
Let's all thank Francisco. It's a beautiful thing, the people who are not only doing a PhD, but they figure out how to make the tools that they need for their work accessible and useful to a much larger community. So yeah, I think a lot of us are looking forward to using this, and it's making what used to be very hard quite doable. Great having you all here, and thanks again, Francisco.
Thanks, Ben.
All
Thank
right,
you for
take
having me.
care.